Ever since the earliest rockets, we've seen them working with a bell-shaped engine nozzle. From the first German V2 rockets right up until the SpaceX Falcon Heavy. But the ubiquity of the bell-shaped rocket nozzle doesn't mean to say that it's the best way to do things. In fact, they have a major drawback, which is one of the reasons why we use multi-stage rockets.
Curious Droid.
However, since the early 1970s, there has been an alternative rocket engine, which has much greater efficiency and was to power the next generation of single-stage to orbit spacecraft to replace the space shuttle. But if it's so good, why hasn't it even been flown yet? The engine in question is the Aerospike, a design that goes back to the 1950s when it was first developed by Rocketdyne. Now, whilst this might sound like an exotic new type of propulsion, the Aerospike is not actually a whole new engine. It's actually just a different way to contain and control the thrust that any rocket, be that liquid or solid fuel, produces, and it replaces the Bell-type combustion chamber. Now, if we've been using the Bell-type rocket nozzle combustion chamber since the very first rockets, right up until now, then what's wrong with them? For a rocket to work correctly and produce enough thrust to lift it into orbit, then you have to control the burning rocket fuel. If there was no rocket nozzle, then the burning rocket fuel would just expand uncontrollably in all directions and very little of it will be converted into useful thrust. What the rocket nozzle does is convert the high-pressure combustion of the rocket fuel into an ultra-high-speed flow of gas exiting the nozzle in one direction and at atmospheric pressure. The ratio of the size of the narrow end to the wide end of the nozzle must also allow for the atmospheric pressure where the rocket will operate. Now, this sounds complicated, but it's actually quite simple. Everything, including you, me, the ground, and rocket engines, have atmospheric pressure pressing on us in all directions due to the weight of the atmosphere as the air is pulled down by the Earth's gravity. If you imagine a column of air measuring 1 square inch or 2.54 square centimeters from sea level to the top of the atmosphere, that air would have a mass of 6.67 kilograms or 14.7 pounds. We don't feel it because we've evolved to live at that pressure. But if you were to go up to 12 kilometers, that pressure would be just 1/10 of sea level. And at 50 kilometers, it will be 1/100th of sea level, simply because the column of air is now much shorter and thus weighs much less. That air pressure also pushes on the gases exiting the rocket nozzle. For a rocket to work at its most efficient and produce the most amount of thrust, the gases exiting the rocket nozzle must be at atmospheric pressure so that they exit out as straight as possible. This is fine if your rocket is travelling sideways through the atmosphere like an air-to-air missile. Then the air pressure doesn't change much. A rocket going into orbit, however, starts at sea level with a lot of air pressure and ends up in a vacuum with no air pressure. Because a Bell nozzle has a fixed shape and size, its maximum efficiency and thrust will only be achieved at one altitude. Design it to have maximum thrust at sea level at takeoff, and the exhaust gases will overexpand and lose thrust at high altitudes because of the lack of air pressure. Design it to have maximum thrust at high altitudes, and at takeoff, the air pressure is so much that it constricts the gas flow inwards, which leads it to separating from the nozzle wall and becoming unstable, usually resulting in the engine blowing up. In an ideal rocket nozzle, it would change its shape as the altitude and air pressure changes. This is what an Aerospike does. It uses the pressure of the air surrounding it to have the same effect as the bell of a traditional rocket engine. The two main types of Aerospikes which have been developed are the annular or round ones and the linear or straight ones. The round ones are where we get the name from. If you imagine an inverted bell shape, it becomes a round spike. This spike becomes one side of a virtual bell, whilst the air pressure surrounding it compresses the exhaust gas against the inner spike. although many now use a truncated spike, which has a much shorter design than the equivalent engine bell. As the rocket goes from takeoff at high air pressure to the low air pressure at high altitudes, the shape of the exhaust flow changes due to the changing air pressure to keep it at its optimum shape and optimum thrust. This is what's called an altitude compensating rocket nozzle. Although it might not be as efficient as a bell at any given altitude, it outperforms them at all others. The Space Shuttle main engines, which were used from takeoff to space, were much less efficient at sea level than they were in space. With a rocket engine like the Aerospike, you could use just one engine that would work efficiently from takeoff to space and avoid the need for multiple stages with different rocket engines optimized for different altitudes, effectively becoming an SSTO or single stage to orbit. So, if these are so good, why aren't they used? To date, no major rocket launches have used an Aerospike, despite much research and development being done during the 1960s and 70s and then in the 1990s. As a follow-on to the successful J2 engine, which was used on the Saturn third stage, Rocketdyne set about developing and building both toroidal and linear aerospikes using the turbopumps and engine infrastructure of the J2. One of the biggest problems with an Aerospike engine is the cooling of the spike. In the toroidal or round design, the spike is long and heavy, which makes it difficult to cool the tip of the spike to stop it from melting. This was mostly overcome with the development of a new copper alloy called Nalloy Z in the 1970s, which allowed longer use at high temperatures. The design was also changed with a truncated spike, with some of the exhaust gases being passed through the centre to achieve a similar result to the long spike but with much less mass. However, the linear version was even more flexible. In this, the round spike is straightened out into a V shape, with the combustion chambers on either side. The beauty of this design is that it can be made modular, so that it can have more combustion chambers added to make a longer and more powerful engine. Back in the 70s, they used combustion nozzles made into small banks, which were stacked side by side on both sides of the V centre. Although Aerospikes were proposed for the Space Shuttle, as the Apollo program was wound up in the early 1970s, development work on the Aerospikes also stopped, and the Space Shuttle went on to use conventional Bell engine nozzle designs. Things stayed pretty much like this for the next 20 years until NASA was looking to develop the next generation of Space Shuttle using an all-new single-stage-to-orbit design. The design brief was to be able to come up with a completely new launch vehicle that would be fully reusable and would greatly reduce the cost of getting into space from $10,000 per pound to $1,000 per pound. Lockheed Martin won the contract to build the revolutionary design designated the X-33, and one of the key features was the use of the linear Aerospike engines. Development work continued on the XRS-2200 linear Aerospike, and by now, with the use of electromechanical nozzles, it meant that the fuel system could be controlled on a nozzle-by-nozzle basis, a bit like the fuel injection on a car. This allowed for much greater throttling control and allowed for thrust vectoring by turning off different sections of the engine. This also removed the need to have heavy, complex engine gimbals. Work progressed well up until 2001, when due to issues with the X-33's composite fuel tank and cost overruns, the project was cancelled, again taking the Aerospike engines with it. Progress has been made with NASA testing small-scale solid rockets with a toroidal full-length Aerospike in 2004, but since then there have been no large Aerospike engine developments. So why don't new companies like SpaceX and Blue Origin use the Aerospike engines with all the efficiencies they bring? Wouldn't they be the perfect match for a low-cost route to space? As far as we know, SpaceX has looked at using Aerospikes, but given the fact that no large-scale Aerospike has ever been flight tested, it would be a very big risk when you're looking to set up a commercial orbital space company. One of the driving principles of the space race was to do the job good enough and no more. Basically meaning that once you have developed your spacecraft or your rocket engine to do what it was designed to do, then that's it. You stop there. The technology SpaceX and others are using is well known and tested. The way they use it might be different, like relighting the main engines to descend back to Earth, but the engines themselves are a known quantity. Commercial companies have to make a profit in the end, and taking on a major task like developing a new untested engine design is something that could quickly sap those profits away. Although the X-33 project almost got them to flight testing, it's still new technology and needs more money and more development. It would also mean completely redesigning the rockets away from the tried and trusted but yet limited traditional bell nozzle engines. All this takes time which could be used launching with traditional engines and getting money into the companies. Although there would be a saving of up to 40%, the fuel is actually one of the cheapest parts of a rocket launch. Elon Musk said himself that the Falcon 9 cost $60 million to build, but only $200,000 to fuel. The bringing back of the boosters and the central core with the engines brings far greater savings than could be achieved with a change to Aerospike engines. It seems as though until the price of launches has been driven down to as low as conventional bell nozzle engines will allow, that Aerospikes will remain on the drawing board. The single stage to orbit vehicles which perfectly complement the Aerospike's capabilities seem a long way off since the cancellation of the X-33 and the renewed interest in returning to the moon using variations of conventional engines that date back to the early 1960s. There are smaller companies like Aerospike, which are developing small-scale Aerospike engines for single-stage to orbit satellite launches. But unless there is a radical change in the space market, only time will tell if Aerospikes will ever get used for future space vehicles. So what does it take to design a rocket engine? How much thrust does it take to lift a spacecraft, and how fast must we launch an object from the surface of the Earth to get it to leave? You can look up the answer if you want, but if you're like me, then you want to create things by yourself. Our sponsor for this video, Brilliant.org, is dedicated to doing just that, turning you into a living, breathing, and most importantly, calculating scientist. Head on over there and prove for yourself just what it takes to get a rocket into orbit. Having a strong math and science skill set is crucial because it opens up so many ways to explore the universe. To support Curious Droid and learn more about Brilliant, go to brilliant.org/Curious Droid and sign up for free. So, if you're ready to launch off a planet, the first 200 people will get 20% discount off of the annual premium subscription.